Power series. What's a power series? Given a real number a that's fixed, a power series in the quantity x minus a, or a power series centered at a, is a series of the form, so it's a series, it's a summation, infinite sum, of terms that look like Cn, where Cn is a constant, times x minus a, that quantity which is part of the name of such a series, so x minus a to power n. Okay? If you want to unravel what this notation means, when n is 0, this means c sub 0 times x minus a to power 0, right? When n is 0. So when n is 0, this is c sub 0, and this is 0, right? And we're going to adopt the convention that when we're talking about x minus a to power 0, then this is going to be 1. Even though x is possibly a, right? If x is a, this becomes 0. So we're going to adopt the assumption that this is actually a 1. Okay, it's a convention. Okay, so what do we get when n is 0? We get c0 times 1, so c0. Okay, now when n is 2, when n is 1, when n is 1, we get c sub 1 times x minus a to power 1. And when n is 2, we get c sub 2 x minus a to power 2, and so on. Okay, so a power series it looks like a polynomial, but the only difference is that it has infinitely many terms, right? Because that exponent keep increasing. Okay, a polynomial is a finite sum. This resembles a polynomial, but we have an infinite sum here. All right, and the x is the variable, so x is a variable, and the cn's are constants. They are called the coefficients of the series. Okay, so the x is a variable. So you can think about a power series. It's actually a function. It's a function in x, and it has a domain, right? Every function has a domain. What does the domain of a function mean? It's the set consisting of all the inputs accepted by the function. Well, what would be the domain of such a function? This is a series, so whenever the series makes sense, for the x that allow the series to make sense, I'm gonna take these x's to be part of the domain, correct? And what does it mean that the series making sense? It means that the series converges. So if you think about this as a function in x, the domain of this function would be the set of all the x allowing the series to converge. Okay, x being a real number. All right. For example, if you think about x being a, if x is a, what is this? This whole thing becomes 0, right? If x is a, this whole thing becomes 0 except the first term, it's c sub 0. And cert, right? What I'm saying is if x is a, if this is a, all this guy is 0, correct? Except for the first term, all the others are 0. So this is 0, this is 0, and all the rest is 0. So the only thing that this equal to becomes c0, and hence it's a convergent series. So when x is a, I have a convergent series, and its sum actually is c0. What I'm saying is that a would be part of the domain of such a of this function, of this series. Okay. All right. Okay, so let's read the comment just below here. So a power series centered at a may converge for some values of x and diverge for other values of x. Okay, as we just discussed. To illustrate this point, choose, for instance, for all n, Cn to be 1 in this equation. Okay, in equation 1, this equation. Choose Cn to be 1. So all of these are simply 1, no matter what n is, right? That's what we're taking here in this context. And observe that the series becomes simply a geometric series. Correct? This becomes a geometric series with common ratio x minus a. And we know that a geometric series with common ratio r converges if and only if that common ratio in absolute value is smaller than 1. Correct? So in this context, this means in the absolute value of this common ratio, which is x minus a in this case, to be smaller than 1, which means x should be between a minus 1 and a plus 1, correct? This means that x is between a minus 1 and a plus 1. All right. So any x that you give me outside of this set is gonna produce a series that's divergent, right? And if you give me an x inside this set, the series is guaranteed to converge. Okay, let's do an example. Find all the real numbers for which the following series converges, and this series has the following terms: n to power n, x to power n. So we want to find all the x that I can replace this x with to get a series that converges. We can run here the ratio, the root test, right? The term here looks like this is nx to power n, right? This guy is nx to power n. So how about the root test? Remember the root test? It allows us to find when the series is going to be absolutely convergent and hence convergent, right? The question is about convergence here. So we're going to take the limit as n goes to plus infinity, right? As n goes to plus infinity of the nth root of the absolute value of this term, and this term is nx to power n, right? Okay, and this is equal to the limit as n goes to plus infinity, the absolute value of nx, correct? So the nth root and the nth power undo each other, so you get this. And then this is equal to the limit as n goes to plus infinity. Since n is going to plus infinity, this means that n is certainly a positive entity, so this means that absolute value is n times the absolute value of x, correct? And what is this? Well, it depends what x is. If x is 0, this is 0. And if x is non-zero and n is blowing up, this product is gonna also blow up, right? So this means two things. This is 0 if x is equal to 0, and it's plus infinity if x is non-zero. Am I correct? One more time. Why this happens when x is 0? When x is 0, no matter what n is, this is always 0, and hence I'm gonna get the limit to be 0 because it's the limit of a sequence in some sense where all the terms are zeros, right? If x is 0. If x is non-zero, this whatever non-zero you take here, then since n is gonna blow up, it's gonna dominate the whole thing. So this is gonna be infinity. Okay. All right. So you get two answers based on what x is. What does it mean? Recall the nth root test, right? The root test. If the limit is smaller than 1, then the series is gonna converge absolutely, right? So when x is 0, the answer to the limit is smaller than 1. 0 is smaller than 1, right? This guy is smaller than 1. So this is smaller than 1. As such, the series is gonna pass the root test, and the series is gonna be absolutely convergent when x is 0. And this is known because, I mean, look, if x is 0, this is the discussion we had in on the previous page. When x is 0, the series is just summation of bunch of zeros, right? Countably many zeros. So certainly the series is gonna converge because the 0 is the center of the series, right? The 0 is the center of the series, correct? In this case, a is 0. That guy in our discussion is 0. So this is why you see x to power n. Okay? All right. So that center is certainly part of the domain of that function, which means that certainly at this point the series is going to converge. All right. Otherwise, the series is divergent, right? Because this is bigger than 1, and the root test tells us that if the limit is bigger than 1, then the series is going to diverge. So what can we say then? So by the root test, the series n to power n, x to power n, is convergent at and only at 0. Correct? That's what we discovered here. Okay. Next. Example 2, determine the domain of the function, which means we want to find all the x allowing this function to be well defined, which means the series being convergent, right? You have this, I mean, you can interchange these two notions, right? X being in the domain of this function, or x being a number allowing the series to converge. These two notions are interchangeable. Okay. All right. So what do we have here? The term do not look like the nth power of something. So I'm not gonna go to the root test. I can run the ratio test. Correct? If I think about this as being the an term, right? If you think about this as being the an term in this context, the an of what? The an of the ratio test. Okay, and you run the test. So you're gonna take the limit as n goes to infinity of the absolute value of the quotient an plus 1 divided by an. Correct? And if this limit turns out to be a number smaller than 1, or if we can make this limit to be a number smaller than 1, then the series is going to be absolutely convergent, and hence such an x is going to be part of the domain. And whenever the limit is bigger than 1, the series is going to be divergent. Correct? And when it's equal 1, we have to check by hand what happens, because the ratio test doesn't produce or doesn't give us any information. It's inconclusive, right? All right, so let's see what this limit is first in terms of x. Obviously, this limit is in terms of x here because the an itself is in terms of x, correct? So this is equal to the limit as n goes to plus infinity of the absolute value of x to power n plus 1 divided by 1 times 3 times 5 times ... all the way to, I'm talking about the an plus 1 term, right? Because this means an plus 1 divided by an. So I'm going to write here an plus 1. So what's the last term in an plus 1? So when n is n plus 1, that's n plus 1, and that's n plus 1. And if this is n plus 1, what happens here? This means 2 times n plus 2 minus 1, so 2 times n plus 1, right? This is 2n plus 1. So 2n plus 1. Do you agree with me? One more time. If you replace n by n plus 1, I'm talking about an plus 1. This means instead of this n, I'm going to have n plus 1. So 2 times the quantity n plus 1. And this means 2n plus 2 minus this 1 becomes 2n plus 1. Agree with that? All right. And then I'm going to divide by an. And what's an? It's xn divided by 1 times 3 times all the way to 2n minus 1. Okay. And don't forget the absolute value. Alright, but dividing by something is the same as multiplying by the reciprocal of the thing, so we get limit as n goes to infinity the absolute value of xn plus 1 divided by 1 times 3 times 5 times dot 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 all the way to 2n plus 1, right? Times the reciprocal of that. And the reciprocal of this is 1 times 3 times 5 times 7 all the way to 2n minus 1. And downstairs is xn. Do you agree with this? Alright, so let's see if we can simplify. Obviously the 1 can cancel the 1. Okay, that's not a big deal. 3 divided by 3. See, they are the same thing. 5 divided by 5. 7 divided by 7. These are odd, these are odd. They are the same thing. But this is one more. Remember, this is coming from an plus 1. So this is the next term technically if this were to continue, correct? So what I mean is that guy 2n minus 1 is going to be found right there. It's going to be found right there. Because an plus 1 is the first term after an, and an has this part in it. So the first, so what I'm expecting is the an plus 1 to contain this part. Why? Because look, so that denominator is starting at 1 and it's ending at 2n plus 1. That numerator is starting at 1 and it's ending at 2n minus 1. But it's visiting, both of them are just visiting the odd numbers, right? What would be the first odd number before 2n plus 1? Well, it's 2n plus 1 minus 2. Correct? The first odd number before this guy is 2 units away to the left. So 2n plus 1 minus 2 is 2n minus 1. So I have 2n minus 1 here for sure. Right? And then if you go one more odd number, you pick up that 2n plus 1. What I'm saying is all these guys are found. All these guys are found here. So they're gone. Correct? And how about these? The xn plus 1 divided by xn. If you simplify them, this is not that hard. If you simplify this guy with this guy, you're only left with x. Correct? Because you subtract n from n plus 1, you get 1, right? So this is simply x. So what do you get then? This limit is equal to the limit as n goes to infinity of the absolute value of x divided by 2n plus 1. Correct? But 2n plus 1 is positive, so this is the same as the limit as n goes to infinity of absolute value of x divided by 2n plus 1. And this is what? This is what? Let's isolate the case when x is 0. When x is 0, we know that the series is going to converge, right? The sum is actually 0 when x is 0. So I'm isolating the case when x is 0 because I'm dividing here by an. So I'm dividing by this guy. And if this guy is 0, right? If xn is 0, then I'm dividing by 0. So let's isolate the case. Let's isolate the case when x is 0. We know it. The series is convergent. Now, when x is not 0, so suppose x is not 0 in this discussion, what happens? We get the absolute value of x divided by 2n plus 1. And what's going on with n? N is going to infinity. N is going to infinity. This means downstairs is going to blow up. As such, that constant divided by something that's blowing up is going to be 0. Correct? And it's going to be 0 for all x different than 0. Makes sense? For all x different than 0. Okay? Because we isolated the case when x is 0, the series is actually convergent. Okay? It's actually 0. Okay, and what do you know about 0? Isn't it less than 1? Isn't it less than 1? So this means that the limit of this ratio is smaller than 1 for all x different than 0. What does it mean? That the series is convergent for all x different than 0. In fact, absolutely convergent by the ratio test, right? So the series is absolutely convergent by the ratio test for all x different than 0, correct? And when x is 0, the series is understood to be convergent, right? The series is also convergent, right? Because we talked about this when we define power series. Power series is always convergent when the x is replaced by the center of the series, right? In this case, the center is 0. Remember what the center is? The center means that guy A, right? So in this case, there is no A, so this means A is 0. And as such, when x is 0, the series is going to converge, correct? All right. So all in all, the series is absolutely convergent and hence convergent for all x. For all x in R, right? Do you agree with that? All right. Example 3. Now we have this series. For what values of x this series is convergent? Okay. All right. So in my case, this is the an. I'm gonna run also the ratio test. So this is gonna be the limit as n goes to infinity of an plus 1 divided by an, and this is the same as the limit as n goes to infinity of the absolute value of an plus 1. What's the absolute value of an plus 1? It's going to be minus 1 to power n plus 1 times x to power n plus 1 over the third root of n plus 1, right? This is the an plus 1. And dividing by an is multiplying by the reciprocal of an. And this is the reciprocal of an. So, oops. So what? So what do we have? What do we get? We get the third root of n upstairs divided by minus 1 to power n xn. Absolute value, right? Okay. Let's try to simplify now. Don't worry about these minus 1s because inside the absolute value they evaporate, right? It absorbs them. Don't worry about the minus 1s. In terms of x, how many x's do I have? If you simplify xn plus 1 with xn, we get x, right? And these guys, we cannot simplify these guys, so they are what they are. So this is going to be absolute value of x times the third root of n. Because it's positive, I'm going to just put it outside the bars immediately. Third root of n plus 1, right? You get this. Okay. And where does this go as n goes to infinity? As n goes to infinity, this is going to 1, right? So, okay. How about, let's push out the absolute value of x, because it's independent of n, right? This would be a constant with respect to n, so you can push it outside the limit, and you get this limit. Third root of n divided by n plus 1, right? And as n goes to infinity, third root is continuous, so that's gonna go inside to 1, This guy, this guy goes to 1. The whole thing is going to go to the third root of 1, still 1. So this is 1. So this is 1, right? So what do we get then? This is absolute value of x at the end of the day. So the limit of the absolute value of the quotient, an plus 1 divided by n, is simply absolute value of x. And what do we know about this? We know that if the limit is smaller than 1, the series is going to converge absolutely. And if this limit is bigger than 1, the series is going to diverge, right? So thus, by the ratio test, the series is absolutely convergent for all x less than 1, which means between minus 1 and 1, right? And so let me actually write it. So that is to say, as long as x is between minus 1 and 1, this is what absolute value of x less than 1 means, right? And is divergent for x an absolute value bigger than 1, which means when x is smaller than -1 and or x is bigger than 1, right? Correct? So diverges if x is something like this or something like this. Very good. Let me just complete this. Okay, so the only remaining discussion has to do with the boundaries, with the boundary points, -1 and 1. What happens at -1 and 1? The ratio test doesn't give us any information about these boundary points. Correct? So we have to check this by hand. So we need to consider what happens at the boundary point, so at the endpoints, separately, right? Correct? So we need to consider those two cases separately. Let's start by x being equal to 1, -1, let's say. So what happens when x is -1? When x is -1, what happens to the series? You see the series? This becomes the series -1 to power n. I'm replacing now x by -1. I'm trying to understand what happens when x is -1. So that guy x is now -1. And here I'm going to have the third root of n. So when x is -1, the series becomes sigma, right, -1 to power n, -1 to power n. As we said, we're replacing x by -1 now. And the series now starts at 1, right? As we know. Am I correct? It starts at 1. Yeah, okay. All right, so I hope you see what we're doing. So we know when x is between -1 and 1, strictly taken between -1 and 1, the series is convergent. And when x is an absolute value bigger than 1, which means x is less than -1 or x is bigger than 1, the series is divergent. We know this. The only remaining cases are when x is equal to -1 and when x is equal to 1, the endpoints. Correct? So I'm checking by hand what happens at -1. I'm going here, replacing x by -1. The series now is a series of constants, right? Because I'm replacing the variable by this number -1, and this series becomes -1 to power n, -1 to power n, divided by the third root of n, Now what is this? Isn't that... So upstairs is minus 1 to power 2n, right? Minus 1 to power 2n, and 2n is even, so minus 1 to an even power is 1 divided by n to power 1/3 downstairs, right? Agree with this? So n to power 1/3. And this is what? This is, isn't it a p series with p less than 1, which is 1/3? So this is divergent. So this is divergent. So which diverges, being a p series with p equals to 1/3, which is less than 1. And we know such a p series diverges, right? Okay. Now what happens when x is equal to 1? The other endpoint, the series becomes what? Now I'm replacing x by 1, so that guy now is simply 1. 1 to power n is 1, right? So we don't have to worry about this guy. And that becomes minus 1 to power n divided by the third root of n. So it becomes an alternating series. So it becomes the alternating series sigma n equals 1 to infinity minus 1 to power n divided by the third root of n. Okay, and if you run the alternating series test, I'll let you do it. If you run the alternating series test, this series is gonna be convergent. Okay, this series is gonna be convergent. Certainly, it's not absolutely convergent. It's conditionally convergent, because if you put the absolute value, you go back to the previous case, right? So this series is convergent by the which is convergent by the alternating series test. I'm gonna just write the acronyms AST. By the alternating series test. Okay, I'll let you do it. Just check this, please. Make sure that this is the case. Remember, for alternating series test, the 1 over third root of n, this term has to be these terms have to be decreasing all the way to 0, right? It's not hard to see it, but just make the case. All right, so x equals -1 allows the series to diverge. X equals 1 allows the series to converge. And everything between -1 and 1 allow the series to converge, right? Allow the series to converge. So what can we infer? How about we highlight it? So I know that the series is convergent, right? The question is about convergent, not convergence, not about absolutely convergent. So the series converges when x is between -1 and 1. This is an information I know. And it converges when x equals 1, right? So these are the good points. And what are the bad points? Let's color them in a different color. Let's say red. The bad points are points that are less than -1, bigger than 1. The series diverges there. And -1 is bad, correct? So if you put all these highlighted information now, what can you say then? So in conclusion, what all this information is telling us is the following: the series converges for and only for x between -1, 1, closed at 1, open at -1, right? Because of the highlighted things. So everything between -1, 1, and 1, because we checked it by hand, is a good point. So at the end of the day, we get that we have convergence here. Okay. Let's make the following observation. in all three examples that we had so far, in all three examples, let's go back to the first one. So in the first example, we had convergence only at 0, right? Only at 0, which is the center of the series. In example 2, we had convergence on all of R, and in the last example we had convergence between -1 and 1, correct? In all three cases, I want you to observe, in all three cases we had convergence in an interval, okay? In an interval, right? Either between in this case was -1, 1. The previous case was all of R, and the first case is 0. Just the single point 0. You can think about the single point 0 as being a collapsed interval, right? So all three cases are intervals where the series converges on an interval, and this interval is in some sense centered at the center of the series, right? What's the center of the series in example 3? It was 0, right? So in some sense that thing is centered. In some sense the center is at 0. It's an interval centered at 0, right? X minus 0 to power n, 0 being the center of the series. So it happens that the convergence is between -1, 1, which is in some sense an interval centered at 0. Even here, we had all of R. Well, all of R is also can be thought of as an interval centered at 0, and in that case, in example 1 is just 0. So it's kind of like having, in all three cases, it's kind of like having 0, which is the center of all three examples, right? All three series, they're all centered at 0. And having some radius, right? Having some radius. If the radius is 0, then having some radius. If the radius is 0, if that radius is 0, this means I have a collapsed interval, so I only get 0, like in this case. In example 2, this radius is infinity, so we have infinity, so that, which means that these brackets go all the way to here and here in some sense, okay? And in the last interval, in the last example, we had R to be 1, right? We were talking about -1 and 1. Remember that? Okay, so this is just an observation, and the question becomes, does this phenomenon occur all the time? So do we always have the convergence centered at, or the points where the convergence of the series happen centered at the center of the series and having some type of radius? Okay, so the next theorem, which is the main result, is going to tell us that yes, this is the case all the time. Let's read the theorem. So for a given power series centered at A, which means a series like this, exactly one of the following properties holds. The first case, the series is going to converge at and only at x equals A, which means I'm going to have a convergence just at A, okay? If you go a little, no matter where you go away from A, you're going to have divergence. The second scenario is when the series converges for all real numbers x, which means no matter what x is replaced with here, no matter what the real number you plug in here, you're gonna have convergence. Let me just remind you that this case occurred in example 1, right? Case 1 here, the first scenario. The second scenario occurred in example 2. And the third case is there exists a real number r, which we refer to as the radius above, that's positive and finite otherwise, such that the series is convergent as long as you are inside this interval centered at A and having radius r, right? And is divergent outside of this ball or this interval. Okay, so pictorially, look at this picture. Let me zoom in so you can see it better. Pictorially, what this is saying is, in all three cases, the first case is r equals 0. Okay, if you ignore that constraint on r for a second, if r is 0, we're talking about all this red part collapsing just to be at a, correct? So we only have convergence at a. In case 2, if r goes to infinity, so you can stretch the red part, right, all the way to infinity, so everything becomes red, which means I have convergence everywhere. And the third scenario is um, there is a finite number r, positive and finite, so within that neighborhood of a, within that interval centered at a, which is the center of the series, by the way, I'm gonna have convergence, and once you are outside, you're gonna have divergence, right? This theorem tells you nothing about the endpoints. I have no idea what happens at the endpoint. Anything can happen, right? Okay. So this r is referred to as the radius of convergence, and the interval of convergence is the interval that consists of all the values of x for which the series converges. So it's the red part here that's referred to as the interval of convergence. Okay, it's the set consisting of all the points that allow the series to converge. And radius of convergence is about how far can you go from one side of R, right? How far can you go while having a convergence? Make sense? Okay, so the observations we made in the first three cases actually happens to be a phenomenon that exists all the time. Let's revisit these examples. Let's revisit them. So in all three cases, as I mentioned, I had this, what the theorem told us. The radius of convergence in the first one is 0, right? Because we had a collapsed interval of convergence. In the second example, the radius of convergence is plus infinity because the interval of convergence was minus infinity plus infinity. And the last example, we had the radius of convergence to be 1, as previously mentioned, because we knew that the points where the convergence happens is the set consisting of all those points between -1 and 1, including 1, right? Okay. All right, let's do this example. The question is, find the radius of convergence and interval of convergence of the series. This is the series now. Well, how about we run the ratio test for this? So the limit as n goes to infinity, if you think about this as being an, so the absolute value of an plus 1 divided by an, and this is the limit as n goes to infinity of the absolute value of an plus 1. I'm going to replace n by n plus 1, so I get minus 3 to power n plus 1 x to power n plus 1 divided by the square root of n plus 1 plus 1, so n plus 2, right? N plus 1 plus 1 is n plus 2. Divided by an means multiplying by the reciprocal of an, and the reciprocal of an is square root of n plus 1 upstairs, divided by minus 3 to power n xn. Okay, let's start simplifying. Let's simplify. So if you simplify x to power n plus 1 by xn, you only get x here. If you simplify minus 3 to power n plus 1, if you divide it by minus 3 to power n, you get minus 3, right? You get minus 3. So technically this and this are going to cancel, right? And then we get the rest. So this is then equal to, don't worry about the minus as you said because of the absolute value, so that's going to be limit as n goes to infinity, absolute value of x, correct, times 3 square root of n plus 1 divided by n plus 2, square root of n plus 2, right? So I get something like this. Okay, and this is equal, what's this limit? 3 absolute value of x, this product is independent of n, so you can push it outside, and if you push it outside, you get 3 absolute value of x times the limit as n goes to infinity of square root of n plus 1 divided by, let's extend this, divided by n plus 2. And what's this limit here? This is 1, right? So that becomes 3 times absolute value of x. This guy is 1, correct? Okay. So we get this. So this limit is equal to that, which means if this is less than 1, I'm going to have absolutely convergence. And if this is bigger than 1, I'm going to have divergence. And at 1, I have to check by hand what happens, right? Okay, so by the ratio test, the series converges if this guy 3 times absolute value of x is less than 1, right? Which means what? Which means if the absolute value of x is less than 1/3, which means if x is between minus 1/3 and 1/3. Do you agree with that? So, right, this is the case. We get convergence here, and by the same test, the series diverges outside of this if absolute value of x is bigger than 1/3. Okay, so therefore, what can you say? I mean, the question, there are two parts of the question. The question is about having or determining the radius of convergence and the interval of convergence, where the radius of convergence is 1/3, right? Because this series is centered at 0, so the interval of convergence is centered at 0, and you can go 1/3 units away from 0 while having, right? While having convergence. So if this is 0, right, you can keep pushing all the way to 1/3 here and here and having convergence. So once you go outside, I'm not talking about the endpoints, I'm talking about just everything in between, and once you are less than minus 1/3 or bigger than 1/3, when you are talking about this, then you get divergence. The question becomes what happens at those endpoints, right? So, but what I'm saying here is that radius of convergence is 1/3. So therefore, the radius of convergence is equal to 1/3. Next, we shall see what happens at the endpoints, right? So what happens at minus 1/3 and 1/3? Because all sorts of scenarios can happen at those endpoints. I may have convergence at both, I may have divergence at both, and I may have convergence at only one point of these endpoints. So we need to check by hand what happens. Let's consider the first case for x equals minus 1/3. Well, when x is minus 1/3, what happens to the series? What happens to the series? So I'm going to replace x by minus 1/3, right? So this becomes, so the series becomes what? It becomes the series that starts at 0 minus 3 to power n minus 1/3 to power n, and the whole thing is divided by and the whole thing is divided by square root of n plus 1, right? And now if you simplify, this is 1 upstairs, so this guy upstairs is 1, and this series then is equal to the summation, and ranges from 0 to infinity, 1 divided by square root of n plus 1, right? And you do it your way to find whether this is gonna converge or diverge. You can compare it to the square root of n, right? 1 over square root of n, the p series. Or you can actually see it, for instance, as a p series. Look, I'm gonna do a substitution. So how about the following substitution? How about we call k to be n plus 1? Okay, let's call k to be n plus 1. And let's rewrite the series in terms of k now. Alright, so I'm going to have a series. Every time I see n plus 1, I'm going to write k. So this is the relationship between my old variable and my old index and my new index. So this is 1 divided by square root of k then, right? Because n plus 1 is k. N plus 1 is k. So that guy downstairs is k, or square root of k. And then if n starts from 0 and it goes all the way to infinity, k starts from what? If n starts at 0, k should start at 1, right? K should start at 1. And this is a p series with p equals half, right? So which is divergent, being a p series with p equals half, which is less than 1, right? Okay, less than or equal to 1. Okay. All right, so when x is minus 1/3, then we get divergence. By the way, if you have a different way to do it, please. I mean, you don't have to do it this way, okay? That's a way to do it. You can probably run integral test or limit comparison test. Okay, so my point is just do it a way to find the conclusion. The conclusion is going to be always, obviously, divergence. Now let's go to the other boundary point. So for x equals 1/3, the series becomes, so I'm replacing now x by 1/3 in the recipe of that function, right? In this function, I'm replacing x by 1/3. And what do I get? We get, once you do the simplification, okay, you know what? I'm gonna write it. So n starts at 0, right? To infinity, minus 3 to power n, 1/3 to power n, divided by square root of n plus 1, right? And now if you simplify, upstairs is simply minus 1 to power n. If you simplify, this guy upstairs is minus 1 to power n, because the 3 to power n and the 3 to power n cancel each other, so the leftover is just minus 1 to power n. So we get this. So we get this. Okay, which is an alternating series, and you can check that this is going to converge by the alternating series test. Okay, by the alternating series test. Let's conclude. So 1/3 is a good point at the end of the day. It's part of the domain of this function. It allows the series to converge. That endpoint is bad. So what's the interval of convergence? We know it used to be between, it used to be all numbers between minus 1/3 and over 3. Now we're gonna invite the 1/3 because the 1/3 is a good point, it turned out. So all in all, the interval of convergence is open minus 1 over 3, closed 1 over 3. Correct? Okay. Example 5. Now the series is like this, same question. We need to find the radius of convergence and interval of convergence. Alright, so same thing. Let's think about this as being an. Let's do the ratio test. The root test here is not as beneficial. So n goes to infinity, an plus 1 over an. Okay. All right. An plus 1 is, I'm replacing every n by n plus 1. So I get n plus 1 times x plus 2 to power n plus 1 divided by 3 to power n plus 1 plus 1. So this is n plus 2, right? For an plus 1. Divided by an, which means multiplied by the reciprocal of an. So I get 3 to power n plus 1 divided by n times x plus 2 to power n. Okay. All right. Let's simplify as much as we can. So the 3 to power n plus 1 and this guy, I'm only left with 3 downstairs. How about this? How about this with this? I'm only left with x plus 2 here, right? And what? That's it, right? So this is then equal to limit as n goes to plus infinity, absolute value of x plus 2. Now the series is centered at -2, so I'm going to have that term, and then divided by 3 times n plus 1 over n. Okay, and this is, as n goes to infinity, this is independent of n, so the limit is going to only talk to this, right? So that guy can be pushed outside the limit. It's independent of n, so that guy goes to 1, so the whole thing is going to go to absolute value of x plus 2 over 3. Okay, and same story. If this limit, which is this, less than 1, then I'm going to have absolutely convergent by the ratio test, and this, if this is bigger than 1, I'm going to have divergence, right? So by the ratio test, the series is absolutely convergent, so it's convergent if what? If x plus 2 over 3 is less than, right? Absolute value of x plus 2 over 3 is less than 1, which means x plus 2 is less than 3, correct? This is less than 1 if and only if this happens. That is to say that x plus 2 is between -3 and 3, correct? Which means that x is between, if you subtract 2 from all sides, you get -5 and 1. Yes? So this is -5. Okay. So for all these x, I have absolutely convergence. And it diverges outside of this. I mean, not outside of this. Outside of this with the endpoints. So which means absolute value of x plus 2 being bigger than 3. So that is if x is less than -5 or x is greater than 1, right? Correct? So the only remaining issue is what happens at the endpoints, and those boundary points, -5 and 1. Let's check. Let's start by -5. So for x equals -5, what happens to the series? The series is going to become, I'm replacing x by -5, so this becomes -3 to power n, right? So the series is going to become summation n times -3 to power n, as we just said, divided by 3 to power n plus 1, right? And this is equal to, if you simplify by 3 to power n, you're going to have -1 to power n upstairs, right? -1 to power n times n, and the 1/3, you can push it outside the summation, right? So this is then equal to 1/3, because again, if you simplify by 3 to power n, you only have 3 downstairs, but 3 has no more n anymore, okay? You can push it outside. It's independent of n. All right, you know what? Let's do it in steps. So certainly you get this. So n times -1 to power n divided by 3. Agree with me? You get this for sure. And then you see this 1/3? This is a multiplicative constant that's independent of this index. So that's in factor to all of the terms. You can push it outside. So 1/3 times the summation as n goes to from 0 to infinity -1 to power n times n, right? And what can you say about this series? What can you say about this series? Well, this is gonna diverge, right? Because of, by the test for divergence, because this guy here doesn't go to 0 as n goes to infinity, correct? So which diverges by the test for divergence, correct? Let me use capital letter here on this. One more time, why we get that this diverges by the test for divergence? Because this guy doesn't go to 0. This guy doesn't go to 0, correct? Since the limit as n goes to infinity -1 to power n times n is not 0. Why? Because if this were to be 0, then since n is going to infinity, it can reach all the even numbers, right? So when n is even, which is part of this discussion, those guys are gonna be just n, right? So which are definitely going to plus infinity. So my point is, if this were to happen, then the other one, if n is go to infinity while being even, should also go to 0. But it doesn't go to 0, as such this can't happen. Makes sense? All right. So -5 is a bad point. This boundary point -5 is bad point, correct? How about now the other endpoint, which is 1? So the series now becomes summation. Let's check the series again. So now I'm talking about x being 1. So 1 plus 2 is 3, 3 to power n upstairs. So n times 3 to power n divide by 3 to power n plus 1, and n goes from 0 to infinity, correct? And then if you divide that, that's going to be equal to, as we did before, sigma n goes from 0 to infinity n, right? If you divide by 3 here, 3 to power n, you get this. And this goes to infinity as n goes to infinity, so this also diverges. So which also diverges by the test for divergence, right? Because again, those guys do not go to zero, obviously, right? Okay. So both of these endpoints are bad, then therefore the interval of convergence is, what do we get? So everything between, I think, -5 and 1, right? Excluding -5, excluding 1, right? Because both of these, we checked them by hand, they turned out to be bad points. All right, did I answer the question? I'm still missing radius of convergence. I could have seen it, I could have concluded it here. What's the radius of convergence? The radius of convergence is 3, right? So it's that interval of convergence is centered at -2. The question is, how far can you go? The idea here is you can go all the way to 3, check the endpoints if they are or not good points, correct? So let me have a picture. So I have -2 as my center, and then you go a certain amount, and the amount is 1/3 here. Sorry, you go 3 units. You go +3, so -2 +3, and you go -2 -3. Correct? This is the 1 guy, and this is the -5. Correct? So the radius is 3 units. The radius r is 3, right? How about I go back and add it? Yeah, how about writing it here? So the radius of convergence is r equals 3. Makes sense? All right. So now we're gonna move on to prove the main result. So we're gonna prove the main result. The main result being what? The main result being this theorem, right? Remember the theorem? This theorem? That's the main result. So we're gonna try to prove that. Okay. And in order to prove it, we need some technical ingredients. I'm gonna need this lemma. Let's call this guy lemma, okay, which is needed in the proof of the theorem. And let's read it. Let alpha be a real number that's not 0. This means alpha is a real number that's not 0. Be given. So let alpha be a non-zero real number that's given. And then the following is going to happen. If the series whose terms are Cn alpha to power n is convergent, then the series whose terms are Cn xn is convergent for all x in absolute value less than absolute value of alpha. And if the series whose terms are Cn alpha n is divergent, then this is going to force the following conclusion. The series whose terms are Cn xn is divergent, and this is for any number x whose absolute value is bigger than the absolute value of alpha. Okay, so let's prove this. Let's call this 1, and let's call this 2. Let's prove 1 first. So let's assume that this is happening. So let's assume that this series is convergent. What does it mean that this series is convergent? It means that those guys, it implies, not means, it implies that those guys go to 0, right, as n goes to infinity. So thus, the limit as n goes to infinity of these guys is equal to 0 by the test for divergence, correct? Because if this doesn't go to 0, then we're going to have the divergence of the series. So this happens. And then what does it mean that this sequence, suppose that these are the terms of the sequence, those terms go to 0 as n goes to infinity. This means that those terms are going to start being in any neighborhood eventually, right? Of 0, any neighborhood of 0 eventually. So pictorially, I'm talking about, I'm just reminding you of what it means for a sequence to converge, because here I have the sequence of those guys. Think about these as being, I don't know, Bn or something. Think about this as being Bn. So they converge to 0, the sequence converges to 0, which means eventually it's going to start, the terms are going to start being in any neighborhood, correct? So the terms of that sequence are going to start being here eventually. How about we take the choice of the neighborhood to be of radius 1? How about we take 1 as being the neighborhood? You can take any number. I'm just taking 1 for simplicity. Then all these bn's are going to be here eventually, right? So all these bn's are going to start being here. So for all n greater than or equal to some rank n naught, correct? Okay, so thus those guys, the bn's, are going to start being here. So there exists a number n naught, a rank rather, n naught, such that for any rank bigger than this, that sequence starts being inside that neighborhood, which means the distance separating this from 0, which means the absolute value of this is less than 1. So now if we take an n greater than or equal to n naught, this n naught that we just found here, what can we say about Cn xn? What can we say about this? Well, I can rewrite this as, how about we multiply and divide by alpha? So we can, by alpha n, Cn alpha n xn divided by alpha n. Okay, so how about we write it this way? I can do so as long as alpha is not 0, right? And alpha is not 0. Agree with this? Alpha is not 0. So I'm dividing by alpha. I can do so. So let me highlight this for you. So this is because alpha is not 0. Okay. And what is this? This is equal to absolute value of Cn alpha n times absolute value of x over alpha to power n. Agree with this? And then what do you know about what do you know about Cn alpha n, an absolute value if n is bigger than or equal to n naught? This is less than 1, correct? This is less than 1 by just because of this. For all n bigger than or equal to n naught, this entity is smaller than 1, right? So and we are choosing n bigger than or equal to n naught. As such, this is smaller than 1. So I get that this is smaller than 1. And this means that this is smaller than the absolute value of x over alpha to power n. Right? So what do we get? We get that these guys are smaller than these guys for all n bigger than or equal to n naught, right? So I'm going to write this conclusion. So this term is less than or equal to this term, actually less than this term, for all n greater than or equal to n naught. This is the conclusion we have so far. And now in part 1, what do we have? They're telling us, under this assumption, so everything we've derived so far is under this assumption, take an x so that the absolute value of x is less than absolute value of alpha, and show me that this is convergent, right? Show me that this is convergent. Let's take such an x. So if we take such an x, meaning if we take an x in absolute value less than alpha, which means the absolute value of x over alpha is less than 1, right? Correct? This is what this means if alpha is not 0, and alpha is not 0. So we get this. So if this happens, then this series, what can we say about this series? X over alpha to power n what can you say about this series? This is a convergent geometric series, right? So this is a convergent geometric series. Why? This is geometric series, and why is convergent? Because the common ratio is x over alpha, which means that guy in absolute value is less than 1. So this is a convergent geometric series since its ratio, a common ratio is less than, an absolute value is less than 1. In this case, it's that guy, absolute value of x over alpha. And then what can we say about the series whose terms are those guys? What can we say about the series whose terms are those guys? By the direct comparison test, those guys are dominated by those guys, and those guys are terms of a convergent series. As such, I'm gonna have the series, the desired series, to be absolutely convergent and hence convergent, right? So so let's put things together. So this is a convergent geometric series. Therefore, so thus, by the direct comparison test, DCT, direct comparison test, we get that this guy from N naught is convergent, correct, by the DCT, because those guys are dominated by those guys, and obviously those guys are non-negative. So by the DCT, for all these n's, right, the series that starts at n0 is gonna be convergent, right? The series whose terms are those guys. Very good. And what can you say then about the entire series that starts at, where does this start at? 0? Let's say at 1. So what can you say about the entire series then? What can you say about the entire series? How about we just leave it like this? The entire series is also convergent because, again, doesn't matter where it starts, because at worst I'm gonna be adding finitely many terms to this convergent series, right? And if you add finitely many terms to convergent series, it remains convergent. So this means that this series is convergent, which means that this series is absolutely convergent and hence convergent, right? Correct? As desired. As desired. This is what they want. This is what they want. If you take such an x, which we did, we're gonna find that the series whose terms are Cn xn for such an x is convergent, and we did this. Okay, so this takes care of part 1. Part 2, we're gonna suppose that this is divergent, and we're gonna show that this is gonna also be divergent for all x in absolute value bigger than absolute value of alpha. Okay, so let me go to part 2. I'm gonna suppose that the series whose terms are Cn alpha n is divergent. Okay, so that's the assumption, and we want to show that. So we want to show that the series whose terms are Cn xn is also divergent for x in absolute value bigger than alpha, right? In absolute value, right? So that's what we want to show. Let's take an x as such. So let x be as such. So let x be in R such that the absolute value of x is bigger than alpha. Okay. An absolute value again. Correct. And if the series converges, what can you say by part 1? What can you say by part 1? Well, if the series converges, then it's gonna converge if you replace that guy. Forget about the name. Whatever this guy is if you replace it by any other guy that's an absolute value smaller than this star guy, right? So whatever you replace this guy with, as long as it's the absolute value is smaller than that star guy, it's gonna be convergent, correct? So what do we have here? So we have that this is convergent. That's the star guy that we have above. Now, if you give me any other number smaller in absolute value than this star guy, if you give me any other number smaller than this star guy, then it must be convergent, correct? Alpha is such a guy. Alpha is such a guy. That's the same star guy, right? That's the same guy. So alpha in absolute value is smaller than the star guy. So by property 1, we have that this series is convergent, correct? If you use property 1 for the x there to be for the alpha there to be our x and for the x there to be our alpha, you must get this, right? Which is a contradiction. So I assume that this is convergent and I get a contradiction. What does it mean? It means that this must be divergent. So what we want is correct. Thus, this series must be divergent. Correct? So if you take an x, let me erase these stars. So if you take an x, a real number x such that the absolute value of x is bigger than absolute value of alpha, we showed that this series must be divergent. This is what we want. And the way we did it again, we assumed that what we want is wrong. So we assumed convergence, and we used property or part 1 that we just showed. And we discovered that this is going to force that this is a convergent, but this is not convergent because they told us that this is divergent, correct? And as such, that's the contradiction, and we're done, right? All right. Next is the axiom of completeness, and it says the following. Every non-empty subset E of R, so every non-empty subset of the real line that has an upper bound M, and what does it mean to have an upper bound? It means what you might think it means. It means that there exists a number M such that it's bigger than or equal to any number E, little e, in that set, capital E. Okay? So upper bound of a set means that there exists a number so that it's bigger than or equal to every number in the set, right? So the axiom of completeness says the following. Every non-empty subset of R that has an upper bound must have a least upper bound L. And what's a least upper bound? Least upper bound means two things. It's an upper bound, so it's this. This means upper bound again, right? So L, this means that L is an upper bound, correct? Which means L is bigger than or equal to any number in the set E. And imagine it on the real line. So what does it mean that this guy L is the least one? The least, I'm talking about the least part. Because upper bound, now we understand what it means. But the least part means that no matter what number you take less than or less than L, let's call it V. In this context, I call it V. So no matter what L you take smaller than V, there exists always a number here that's in E. Okay, that's what it takes for L to be the least upper bound, which means there exists no smaller upper bound. There exists no smaller upper bound, which means no matter what number you take smaller than L, you can always find an element. There exists always an element in the set E. Okay? All right. So the axiom of completeness is, in some sense, it's telling us that there are no holes in the real line. Okay? There are no holes in the real line. Anyway, so why this is useful in our discussion? Back to the main theorem. Remember the main theorem? I just changed. If you go back to the main theorem, let me take you back there. I'm changing. It's right here. I'm changing this guy. I'm calling it something else. Okay, I'm calling it X there. Think about it as Y or something. Okay, so I'm talking about, just for simplicity, I'm talking about this X minus A to be a new letter Y. I called it there X. Okay, so I get this. And how would you read the remaining? How would you read the remaining part of the theorem? Well, this means X equals 0. This becomes X and R, and this becomes, instead of X minus A, I'm gonna read it over there, absolute value of X here, right? Remember, I'm taking X minus A to be a new letter. You can call it Y. I called it X in my restatement of the theorem. Okay. Anyway, so this was the theorem, and the question is, how do we prove it? The way I'm gonna prove it, look, the nature of the conclusion. You see this conclusion here? It's made up of three things. Either this is gonna happen, or this is gonna happen, or that's gonna happen, right? So it's at least one of them is gonna happen. All right. The way I'm gonna prove it, I'm gonna assume that two of them fail to happen, and I'm gonna show that the last one is gonna offset that the failure of the two. Okay, so I'm gonna assume two of them fail. I'm gonna assume that the first two fail. So I'm gonna assume that 1 and 2 fail. Correct? If you assume that two of them fail, you have to show that the third one offset these failures. That's what it means, because the conclusion of the theorem is made up of three statements joined by this conjunction or, right? Which means that at least one of them should happen. So if you suppose that two fail, the third must happen, right? That's what I'm saying here. So assume that two of them fail. We want to show that the third one, which is in this case part 3, holds. Make sense? All right. So one and 2 fail. What does it mean that one fails? What does it mean that one fails? One fails means what? So what's one? One means the series only converges at 0 when X is 0. So for that to fail, it means there exists another number where it converges, right? I repeat, if one fails, and one being the series converges only at X equals 0, for that to fail, it means I have convergence elsewhere, correct? So this means there exists some number, I don't know, u, different than 0, such that the series Cn un converges, correct? So this is what this means. And what does it mean that 2 fails? What does it mean that 2 fails? Well, what is 2? 2 is the series converges for all r, for all x and r. So for any number x you plug in, this part 2 is you have convergence. If this fails, it means there exists nx and r. There exists nx and r and number x where I have divergence, correct? So this is equivalent to saying that there exists some number, I don't know, y maybe, and r, such that this guy diverges. Does this make sense? So if you assume one fails, it means there exists such a u, and if you assume that two fails, then there exists such a y. Okay, and now we need to show that 3 holds. Okay, let's introduce a set D, which is the domain of this function. The domain of this function. What's this? What do I mean by domain of this function? It's the set where this is gonna make sense, where this is gonna converge, right? So let D be the set of all numbers such that the series is gonna be finite or convergent. Okay. So where this is gonna converge. Okay, so let D be as such. Is D non-empty? Is this set D non-empty? Well, it is non-empty because U is there, right? U, the number U is there, correct? I assume that, even 0 is there. So 0 and U are in D, right? Both of them are in D. Correct? Whose U is the guy that I know here, right? So this series converges when you replace X by U. So certainly U is in the domain D, correct? Because it allows the series to converge. And 0 as well, because look, if you replace X by 0, you get the convergence as well. Okay, so D is non-empty. Does D have an upper bound? Does D have an upper bound? What can you say about a number X? So if X is a real number such that X is greater than the absolute value of Y? What can we say about this? Well, what do we know about the series when you replace X by Y? You get the divergence, right? And if you go back to the earlier lemma, the lemma here, replace alpha here by Y, the Y that we have in the theorem. Replace this guy by Y. If you take an X, an absolute value bigger than the absolute value of Y, what can you say about the series? It's gonna diverge, correct? So since we know that this is divergent, if you take an X, an absolute value bigger than the absolute value of Y by lemma part 2, I'm gonna have divergence. Am I correct? So let me take you back there. So then the series Cnxn is divergent. Okay. All right. So what does it mean? It means if you take a number, an absolute value bigger than the absolute value of Y, you get divergence. So any number in D, so for any X in D, any number you take in D, which means you have convergence for such a number, right? It cannot be bigger than the absolute value of Y, because if it were bigger than the absolute value of Y, that series is divergent. So an X in D must be less than or equal to the absolute value of Y. You agree with this? So we must have this. So we have this. I'll repeat why. Because by lemma 2, okay, maybe I should say then by lemma part 2, by lemma above part 2, if you take such an X bigger than the absolute value of Y, the series must be convergent if you replace X by, if you plug in here that X, right? Okay, so as such, any number in the domain of the function, any number in D, such a number is going to allow the series to converge, right? Any number as such is gonna be at most absolute value of y, because if it passes that value, you start getting divergence. Okay, so what does it mean? This means that every number in D is bounded above by the absolute value of y. Correct? Every number in D is bounded above by the absolute value of y. So thus, absolute value of y is an upper bound of D, right? Correct? Or for D, I should say. For D. Okay, so what can we say at this point? We can say the following. The function has D as its domain, and that D is non-empty, and it has an upper bound. So if you go back to the axiom of completeness, every such a set, every set that's non-empty, you see non-empty, and have an upper bound must have a least upper bound. Okay? So by the axiom of completeness, so therefore by the axiom of completeness, D must have an upper bound. And that upper bound must have a least upper bound. So it must be the smallest among all of the upper bounds. Okay, that's what I mean. The least upper bound. Okay. Let's give it a name. Say R. I called it R because that's the R that I want, actually. Remember in the conclusion of the theorem? That's the R I want. Can you make the case that R is positive and finite? I'll leave to you as an exercise to make the case that R is positive and finite. I'll still talk about it. R is positive because of this U. Because of this U, R is going to be positive. Think about it. And R is finite. R is finite because I know that R must be less than or equal to the absolute value of y, right? And y is a real number. Correct? So I'll leave this as an exercise for you. So y is R finite and positive. Okay, so I gave you the ingredients, just put them together. Very good. So now I want to show that part 3 holds, right? I want to show that part 3 holds. So I got my hands on the R. Now I want to show you that if you take an x in absolute value less than R, you get convergence of the series, and if you take an x bigger than R, then you get divergence of the series. Okay? Let's take an x. So let's take an x in absolute value less than R. Since R is the least upper bound, remember least upper bound? So we gave a picture on the previous page. So this is R. Absolute value of x is somewhere here. So since R is the least upper bound, this guy cannot be an upper bound anymore. As such, I'm going to be able to find an element. I'm going to be able to find an element here. I'll call it alpha. That's in the set D, right? Because R is the least upper bound, so there is always a number alpha in any opening, and that number is in the domain, is in the set D, right? Okay, so since R is the least upper bound for D, there must exist a number alpha in D such that absolute value of x is less than this alpha. Correct? And since alpha is in D, it means that the series, if you place x by me write it for you. So this means that this series is convergent, correct? Yes. All right. And then what can you say by lemma part 1? What can you say about this x here? Certainly alpha is less than or equal to its own absolute value, right? So now read this. That guy x in absolute value is smaller than the absolute value of alpha, and alpha is allowing the series to converge, right? Let me take you back to that page that I was alluding to, the lemma. So I'm talking about alpha here. That's allowing the series to converge, and I'm giving you an x. That's an absolute value smaller than that absolute value of alpha. So what can you say about the series? The series is gonna converge, correct? So the series is gonna converge. Okay. So thus, by lemma part 1, the series Cnxn must be convergent. Okay, and this is what you want. For such an x. Now the last conclusion is, if you choose now an x in absolute value bigger than r, you want to show that the series is divergent. Correct? So finally, if the x is chosen to be bigger than the absolute value of r, I want to show divergence of the series. Well, note that this such an x cannot be in the domain, right? If x is here, x cannot be in the domain D. Why? Because, look, I'll leave it as an exercise, but I'm gonna say why. Because if it were to be in D, then the previous lemma part 1 is gonna tell us that this r is not the least upper bound anymore. Okay, so think about this, please. So again, if x were to be in D, then by lemma, the previous lemma part 1, we can infer that there exists a number in D bigger than r, and as such it's gonna violate the fact that r is the least upper bound. Okay, all right, and therefore the series Cn xn is divergent as desired, right? So what did we do? We showed that if we choose an x in absolute value bigger than r, then the series is divergent, and hence we show the theorem, right? We show the main theorem of this section. We assume that 2 of the 3 statements making up the conclusion fail, then we force the third to hold, right? In this case, we assume that 1 and 2 fail, and we showed 3, which means we were able to find a real number r that's positive and satisfying these 2 conditions. If you give me an x in absolute value smaller than r, then the series sigma n Cnxn is gonna converge. And if you give me an x in absolute value bigger than r, then that thing is gonna diverge. Okay? All right, so this completes this section.